Okay, so in the last lecture we mentioned that there are two different ways or two different main methods or strategies to design a discrete controller. In this lecture we will study those two methods a little bit more deeply. So if you remember that in the first method we had three basic steps, and the first step was that we start with designing a continuous time or analog controller, right? So that was our first step in the design, and then we discretize this controller. So we start to discretize the controller, okay, and the final step is to implement this discrete version of the controller. Okay, but there is a small problem in this strategy. What is it? The point is that, okay, you are designing the controller in the continuous time domain, but eventually in the real system, the final system will look something like this. So if this is the actual your digital controller, so the output is gonna pass through a digital to analog converter, and then to the system and whatever feedback sensor you have here, and back to the input. So something that we have not considered is the effect of the digital to analog converter. So the output from the continuous time controller, or from the discrete controller, is some discrete samples like that. But then after the digital to analog converter, if we use like zero order hold, for example, you will get something like this. So it's gonna be like a staircase shape like that. and this is something which is basically inherent in this discrete controller. So and it's an effect that we have not taken into consideration while we are designing our continuous time controller. So we started our continuous time controller design without actually taking this effect into our consideration. And the drawback from this is that this zero order hold effect is actually introducing some delay to the signal. So it's not the exact version of the signal. So there is, in many cases, there's some lag. You're lagging behind the true signal, and this lag that is happening is somehow taking from your system phase margin, so it might induce some additional instability based on the sampling time that you're using. So what we need to do is we need to modify this step 1 to include the zero order hold transfer function, okay, in our design. So we don't want to design our continuous time controller without taking this zero order hold transfer function into consideration. So that means actually that we want to find the transfer function of the zero order hold in the S domain. So we need to have a continuous time version of the zero order hold. And in order to obtain the transfer function of the zero order hold, so the transfer function, we know that the transfer function is the Laplace transform of the impulse response. So the impulse response of the zero order hold is quite simple. So if you have an impulse, that's the input of this block, so it is applied to the zero order hold, and what you get from the output is a pulse like this. So if this is at 0, so this is what you get from the output. And it's if you want to write down the impulse response of this block, so it's as simple as that. So it's just u of t minus u of t minus t capital, right? So this is the equivalent of this one, and therefore, if you want to obtain the transfer function of the zero order whole, so it's gonna be 1 over s minus 1 over s times e to the minus st. Okay, so this is the transfer function of the zero order whole. So this is the zero order whole transfer function that we want to include. So we want to consider this transfer function in the S domain while designing our continuous time controller. So what we need to do is the following. So in the beginning we have our controller, which is GC of S, which we want to design, but we also need to add this zero order whole transfer function, and then our system G of S, and then our sensor H of S, and that's it. So once we have this set up, okay, so we know the G, we know the H, and now we know the zero order whole. So the task becomes how to obtain this controller transfer function, and we can obtain it using the method that we described earlier. But there is still a problem, and the problem is that if you look at this transfer function, okay, if you examine this transfer function a bit more closely, you will find that there is a nonlinear term here, which is e to the minus st. So this is nonlinear, okay. And the problem with such a nonlinear term is that it's not compatible with our linear control theory. So all of our control theory so far is based on linear control theory, okay. So this is not compatible now. So we need to find an equivalent transfer function. We need to find some equivalent transfer function of the zero order whole and place it instead of this one, so that it's somehow compatible with the with our linear control theory. So this becomes the next important task, and this is actually where the Paddy approximation is quite useful. So what is the Paddy approximation? The Paddy approximation just says, okay, so the Paddy approximation, what does it say? It's as simple as that. So it just says, okay, you can replace this e to the minus st, you can replace it with minus t over 2 times s plus 1 over t over 2 times s plus 1. Okay, so if you do first order rational function approximation of this term, you will get this this structure. And this is now, because so this was the problematic term. We had a problem with this e to the minus st. So if we replace it with this rational transfer function, which is composed of 1 0 and 1 pole, now you can actually use that here, and you can apply all your linear control theory without any problem. Okay, moreover, actually this Paddy approximation, okay, it can be, as I said, it can be used up to for the zero order function. It can also be used to model any delays in the system. So if you have any delay in the system, okay, sometimes you have some certain delay with delay t, for example, in any block of those. So you can model those delays also using this Paddy approximation. Okay, so the next part is we want to just derive this expression just to make sure that we understand it properly. But this is how we're going to proceed in this phase. Okay.